Hello. In this installment of the Patina video series, we're going to be talking about using the debugger and the Patina core. Before we dive in, we're going to discuss a little bit of how this is implemented in Patina. The Patina debugger is implemented in software. This is sometimes referred to as a kernel or a self-hosted debugger, where all of the logic for understanding and communicating with the debugger application lives within the exception handlers. Now, there's a few different components we're going to be referring to throughout the video. There is the core logic. This is what will be accepting the exceptions. It will be reading memory, interacting with registers, inspecting other state on the system, and generally performing the actual actions on the system for the debugger. Then there's the GDB stub. This is the software layer that provides the GDB remote protocol. The remote protocol is a text-based communication that the debugger application and the debugger itself will use to communicate. Then there's the transport. This is both the physical link for the UART as well as the software abstraction for communicating over that physical link. And then there's the debugger application itself. This is on the host machine. This could be WinDbg, GDB, LLDB, or some compatible client that understands the GDB remote protocol. When an exception occurs, this will break into the debugger. The debugger will start to read out state. It will send a notification to the debugger application through the GDB stub over the transport to inform it that the breakpoint or step or some other break has occurred. At that point, the debugger application can send commands to query various states so that it can build up its understanding of where modules are, what registers are, what local variables exist, etc. And then at some point, when the debugger application, or really the user, decides to resume execution, step, go, whatever it may be, it'll send that command to the debugger. The debugger will then return from the exception, and execution will resume as normal. When it comes to the debugger application and the associated tools, we primarily recommend using WinDbg. The reason for this is WinDbg is a pretty robust system software debugger and has support for the GDB remote interface. And one of the main things is it also has native support for PDB symbols, which PECOF images use. Now, because this is the primary use case, we have been investing the most in the tooling for WinDbg, and this comes primarily in the form of the UEFI extension, which is an extension when loaded into WinDbg, allows you to enumerate Patina and UEFI environments in a more robust way. This lets you find the modules automatically, and it lets you do many custom interactions with UEFI, such as tools for parsing various UEFI structures, and then also custom interactions that let you do things like break in when a specific module is loaded. Now, because we do have a generic and open protocol, you can use GDB and LLDB. We have not been investing in tooling in these as much just because it is not a primary use case, but it does work. It has been tested. We would more than welcome contributions for tooling in this department, but today it is not as robust. And with that, we're going to walk through setting up the Patina debugger.
So to get started, we're going to be looking at adding the debugger to Q35. I went ahead and removed the existing implementation so we can walk through the various steps together, but for those who care, there is an existing implementation. So the first thing you're going to do is you're going to declare yourself your static debugger. And the reason that it's static is because the debugger acts as an exception handler, which means it has to live outside of the normal lifetime rules that exist. And so having it static is really the only way forward. So we define our Patina debugger, and in this case we're going to be using a UART 16550 serial port. So now that we're instantiating it, we do a new one, and we provide our serial port. And again, in this case, it'll be a 16550 IO based with a base at our debug port. And with that, we have a basic instantiation of the debugger. Now, it exists, but it's not being used yet. But before we do that, we're going to want to do a little bit of configuration. So to see the full configuration, I would definitely recommend looking at the docs for the Patina debugger crate. But there's a few things that are worth noting. First, log policy. In this case, we actually have a different serial port that we're using for the debugger than we are using for the logging. And for that reason, we can actually be a little bit more loose with our debug policies. So if we go to our Patina debugger logging policy, you'll see we have a few different options. The normal one that people will use is suspend, which means that when you're in the exceptions, it'll disable all logging. This, if you're in the cases where you're using the same serial port for both logging and the debugger, that's really necessary because otherwise the logging can confuse the debugger interactions. Now, there's also disable logging, which means after you break in for the first time, it'll be disabled permanently. This is the safest option if you're experiencing reliability issues, but generally it's not needed. Now, in this case, because we have two different serial ports, I'm actually going to go with full logging, which means that it will not suspend any of the logging. And then, one very important thing is you have to enable it. Just because it exists does not mean it is enabled. Now, you can do this dynamically. That is a platform decision because doing so safely is really up to the platform for them to decide their configuration story. But in this case, I'm just going to force it to be enabled, which means it'll just be enabled always. Okay, now we have our debugger, but we have to actually set it. So before we call the core's entry point, that part is very important, we need to make sure to do set debugger with our debugger. And that's it. The debugger has been configured. So the next step for us is to flash the device and start booting up. So this is when you would usually, do whatever proprietary flashing mechanism exists for your device. In this case, it's just QEMU, so I'm just going to build and run it. All right, it is starting to boot up. And so here we have the logging traffic coming out of our standard I/O. And you'll notice at some point it will stop and say initialize and debugger and initial breakpoint. This means it has taken an exception and it is now waiting for communication from the debugger application. So at this point, we can get our tools set up and start talking to the debugger itself. Now, the first thing we're going to do for setting up the tools, if you go to the Patina book and you go to debugging, WinDbg debugging, there's all the instructions you need for setting this up, and I'm just going to follow those now. So first thing I'm going to do is install WinDbg. And while that's installing, I do want to call out the serial port forwarding. So in this case, we are using QEMU, which exposes the serial port as a TCP port. But when you're using a physical serial port line that exposes as COM or, say, a named pipe, you have to somehow convert that into a TCP port because that is how WinDbg and other debuggers know how to communicate, at least on Windows. And to do that, we've provided this COM to TCP server. The details here might change. I will definitely refer you back to this page because this will be kept up to date. But this allows you to take a given serial port and to then present it as a TCP port. Additionally, this lets you actually view the logs as you go, which if you connect directly to a port, you won't necessarily see that traffic because it'll be eaten by the debugger. But using this script, you can see both at the same time, which means you can observe both your logging traffic and still use the debugger at the same time. All right, WinDbg has been installed, so we will launch it. Now to connect, because this is already exposing a serial port, I go to attach to kernel, go to EXDI, select UEFI. You don't actually have to choose the architecture, but I will here just for demonstrative purposes. And then I will type in the port that is being exposed and then break on connection. For the sake of demoing, I'm also going to show packet log. You don't need to do this. I just want to show what's actually happening under the hood. So we do attach. And here's the traffic log. So you can see that the debugger is communicating. There's an initial break. There's some register reading. There's memory reads, etc. And we now have access to the system. We can view the disassembly. We can view the stack, though it doesn't actually know where we are. So lm list modules, you'll see that it doesn't actually know where anything is. And the reason for this is that it doesn't have the symbols loaded. So a couple things we need to do that. This is where the UEFI extension mentioned earlier comes into play. So on the book again, there's a quick link for installing it. So I'm going to do that. This just downloads the pre-built DLL from the UEFI debug tools repo. And then now that I've done that, I can come in here and I can do bang UEFI extension.init. And this will initialize, it'll find our modules, and we'll see we are in QEMU Q35 Dixie core. Now, we still do not have symbols loaded. The reason for this is, even though it now knows where the module is, it has to find the PDB file to be able to properly assess what the module looks like. So to do that, we're going to come in, we're going to find the build directory for our Patina Dixie core, in this case, and target x64, and we'll see here, we have the PDB file. So we'll grab this path, add .sim path, symbol path, and then we're adding to the symbol path that. And you'll see now we have symbol resolution, we have private symbols for our module, we can see our stack, and we can even walk up and down our stack. So this is the basics for breaking into the breakpoint. And then from here, WinDbg is a little bit of a learning curve. There's a lot of different functions you're going to need to know. I would encourage you to explore various tutorials on that. We also do have a quick cheat sheet on the bottom of this page that'll be pretty useful. One of the things I will really refer people to in general is look at the UEFI extension help. This will be kept up to date and provides various different functions that you're going to need to be able to interact properly with the core. Next, what we're going to do is we're going to start trying out some more robust features of the debugger. So one of the things that's going to be pretty useful is something called a module break. A module break is something exposed by the UEFI extension, and it lets you to break in when a specific module is loaded. So for example, if I want to break in when PCD-Dixie is loaded, I'll set the module breakpoint. You can see the ones that are loaded by doing that again. And then if I continue by typing go or pressing go up here, we will execute, and then we'll break in. See, so now we've broken in again. If I do list modules, you'll see now we have actually loaded PCD-Dixie. So in this case, if I want to inspect the symbols for PCD-Dixie, I would do this, and we'll see that I'm also getting symbols for PCD-Dixie. Now, one of the things you'll notice is the symbols for these automatically resolved, but the Dixie core didn't. The reason for that is that the actual debug info within the PE might or might not have the fully qualified path. In the case of PCD-Dixie, it does. However, in the case of the Dixie core, for us, at least in this compilation, it didn't, which is why we had to add that to the symbol path, and we didn't in this case. So you'll see that I don't have anything for the actual PCD-Dixie here. It just picked it up because I built it on this machine, and the path was already built into the PE image, so it found it automatically. Now we're going to try some more things. So I'm going to first reboot, which is again a built-in command in UEFI extension. And we will see that we are actually rebooting. And then we break in again, at which point I will do, just to be clear, I'll do UEFI extend init again. And we're back at the breakpoint. We're back at the initial module. There is no other modules loaded. The next thing I'd like to demonstrate is something called core reload. There is an article that exists within the Patina book for this. I would refer people back to this. It is basically a function that lets you reload a new version of the core on an existing system with the debugger connected. This is useful for quicker iteration because it allows you to try out changes without actually having to reflash the image, or in the scenarios where it might be difficult to reflash it, just lets you load a binary in a volatile way to attempt and see if changes have worked the way you wanted to, etc. So to do this, you are going to need to find your new module, in this case in the same path as before, except for we're going to grab the EFI, copy its path. So you do load core, and then we will remove the quotes because it doesn't like quotes. That'll probably be fixed here soon. And then we are compressing the image, transferring the image. This usually takes about 20 to 30 seconds. It is worth noting that on a slower UART physical port, this might take longer. And additionally, it is also rate limited when you go through COM to TCP by default. And the reason for this is not all serial ports properly track full buffers and communicate that. And so sending too much information at once can potentially overload the UART. So if you're on a high baud rate serial port, it might be rate limited slightly to avoid sending information faster than the debugger can process it. So what you will notice now is we are actually, it looks like we didn't move, but we're actually at a different address than we were before. This is because it loaded the new module into memory, did the relocations and everything necessary, fixed up the hobs, and then jumped to the entry point of the new module and resumed execution, which means we have actually gone through the initialization of the core again, and we are now at the break, or we're now in the exception handler and the debugger of the new core, not the old core, which is why our addresses have actually changed. And if you notice that our break instruction is also now at a different address. And so we can continue and we will boot as normal. And this is a basic demonstration of the debugger. It is a fairly robust tool. We have spent a lot of time working on it. Obviously, there's a lot of room for growth. I would encourage people to check out a few things. First and foremost, the Patina page, the Patina book. There's also the UEFI debug tools repository. This is where we build UEFI extension as well as a Patina extension that lets you do other more robust things within Patina, such as printing out the GCD and these more complex structures. If you want to get involved in the tooling here, we would definitely welcome more additions for LLDB and GDB in this area. And then lastly, I would definitely look at the Patina debugger docs. So in here, you'll find all the information you need for setting it up, as well as importantly, keeping an eye on the different configurations that are available. You can customize timeouts, exception types you want to break on, log policy, and force enable as we mentioned, and this will probably continue to grow. We welcome plenty of questions and feedback in the Patina repo, and if there are any feature requests, please file issues. Otherwise, we hope that this is helpful for your development. Thank you.